bit about asymptotes. So when we're drawing our curves, remember curves always bend towards the asymptotes. Curves never cut the vertical asymptote because that's an exclusion in the domain, so x can't exist there. However, they can cut these horizontal or oblique ones because that's purely telling us what happens out of the extremities, out at plus or minus infinity. If we have what we call a rational function, so a fraction involving polynomial and a polynomial, we can do a polynomial division, and when it's in that form, it gives us a lot of information. The bottom of the fraction, that's how we find the vertical asymptotes. Bottom of the fraction can't equal 0. The quotient, that will end up being the horizontal or oblique asymptote, whatever that equation is. And the remainder in our polynomial division, that will tell us if it does cut the horizontal or oblique one. So we solve that equals 0, and if there's a solution, then we know that, okay, that's where it'll cut it. So here's one, it's already factorised for me to save some time. Let's do the division. Actually, it probably didn't save me time because I had to expand it out anyway so I could do the division. But anyway, let's do the division. And we end up with, well, x squared goes in x squared once, then we have a remainder of x minus 5. So we could rewrite it like that. Now, once it's in that form, I can see that the x-intercepts will be minus 3 and 2. X-intercepts happen when y equals 0. So before I break it up, I just look at the top of the fraction there, make that equal to 0. Let's plot those 2 points. Okay. The y-intercept is always the constant number, or you can substitute in x equals 0, we get 6. Vertical asymptotes, the bottom of the fraction there, we got them at plus and minus 1 as well. Let's put those in. Horizontal asymptote will be y equals 1. And the last thing to do is to work out whether it cuts that or not. And in this case, it could cut it, yes, at x equals 5. So I now know all these points, it bends towards the asymptotes, pretty much tells me exactly what it's going to do. The only place it cuts, the horizontal asymptote, is over there at 5. Therefore, if it's going through minus 3, it's impossible for it to be up here, because it can't get to minus 3. So we must be down here, and we bend towards the asymptote. So it looks like that. Now, in the middle section, it goes through 6. It must have a U shape going up, because again, it does not cut the horizontal asymptote down below. So it must go away, like so. Now this right hand side is interesting because it does cut the asymptote here, but it has to go through 2. So it must bend towards this asymptote, go through 2, goes through 5 as well, but the horizontal asymptote is telling me what happens at infinity. So it's going to go up a bit, but then it must turn back down so it can go to the asymptote, and this is going to look really dodgy. But something like that. So it's going to go up and then come back down and go towards the asymptote. Okay, let's have a look at this one. So similar thing, let's do our division. X squared goes into x cubed x times. Now x squared goes into minus x squared, negative 1 times. And there's our remainder. We can rewrite this one as x minus 1 plus 4x minus 4 over x plus 2x minus 3. Let's get all our information. X-intercepts go to the original equation. We've got 3 of them. Let's plot them in. 2, 1 and negative 1. Y-intercept is negative 1/3. Vertical asymptotes, bottom of the fraction, negative 2 and also at 3. We have an oblique asymptote this time at x minus 1. So we draw in y equals x minus 1. I kind of don't need to ask the next question, does it cut? Because I can see it already does because of where it was. But let's confirm it. Sure enough, if I solve the top of that fraction, we get x equals 1. Okay, so we're going to go through all of these points. Starting at the left-hand side. Well, again, there's no x-intercept here. So it can't be on the top of this oblique asymptote. It must be below. So in this little triangle down here, so I must do something like that. Okay, let's go the other side. It's got to go through minus 1. It goes through the y-intercept here. That tells me it must be coming down because it can't cut the oblique asymptote down here. We haven't got a point of intersection there. So it must be coming from the top. It must go down. It goes through minus 1/3. It's got to go through 1. Then somehow it's got to come back to 2. But it doesn't cut the oblique asymptote. So it must go underneath it, come back down, and then go to the asymptote again. Okay, now the far right, we've got a similar situation to what we had over here on the left. It doesn't have another x-intercept, so I must be trapped in that triangle up the top there. So that's a bit about asymptotes. And I guess anytime we have some sort of reciprocal function, so something involves a fraction, we're turning it upside down because bottom of the fractions can't equal 0, we're going to get asymptotes. So let's look at this idea of turning graphs into reciprocal functions. If I want to draw 1 over a function, how do we do it? Well, first we draw the original function, and then we look for some key information. So when I turn it upside down, I know the bottom of the fraction can't equal 0. So whenever function x, the original function, is equal to 0, in my new picture, I must have a vertical asymptote. This is just some random function. I tried to get every sort of feature I could think of. I've got a horizontal asymptote there, I've got a vertical, I've got some turning points, x-intercepts, things like that. That's what we're going to attempt to turn upside down. Now, if I knew the equation of function x, easy, I could work out exactly what it was. I don't here, it's just some random curve. So I want to turn this upside down. So we just said all of those x-intercepts will become vertical asymptotes. So I've drawn those in. What else happens? The reverse will be true. If the original curve is going to infinity, so if the original curve had a vertical asymptote, then it's going to become an x-intercept because we're going to turn it upside down. It's going to become a sort of x-intercept. I've got a vertical asymptote over there. This will now become an x-intercept, but you'll notice I've just drawn a hollow circle to indicate that point is not actually included. Because if it wasn't in the domain of the original function, it can't magically become in the domain of my new function when I turn it upside down. Whatever this new graph is, there'll be a point discontinuity here at the x-intercept. Okay. Oh, some other points I plot in. You turn 1 upside down, you get 1. So I know that those points on the original curve will remain. They're not going to change. Same with -1. So let's plot in -1. We're going through those points. Now, here, the horizontal asymptote, I don't know exactly what number it is, but I do know it's smaller than 1. And if I turn a number smaller than 1 upside down, I'll get a number that's bigger than 1. So I've placed mine bigger than 1. So there it is, up there. If the original graph is increasing, then the reciprocal graph should be decreasing. And the other way around as well. The sign's not going to change. You turn a positive number upside down, it's still going to be positive. Turn a negative upside down, it's still going to be negative. So that will stay the same. So let's go back to our graph here. What does that tell me? I know the curve has to go in all of these sections. Now why did I stop? You see, let's work from the left. On the left here, from this point, it's always below 1. Turn it upside down, it must go above 1. However, it can't cross the horizontal asymptote because the original one didn't cross the horizontal asymptote. So it must stop there. Then I go to the next section. With the next section, it's always above 1. So this one's always below 1. But look, this one does cut the horizontal asymptote, so this one can cut the horizontal asymptote. So it'll go all the way down to the axis. It could be any positive number in there. It's going to stay positive. Now, the next little section, we're always, oh here it is, we're always below this point. So when I turn it upside down, I'm above this point. Then the next bit is in between these two red dots, but some's positive, some's negative. So let's just look at this negative bit. It's always above this red dot, so I end up below the red dot. Then I go to the next section, it's below the red dot, so I end up above the red dot. It cuts the horizontal asymptote, so this one can cut, it could keep going. And the next one in between these two red dots, I get something that's always above 1. Again, it cuts it, actually cuts it twice, this one. And so we can go below, and we'll go all the way to the axis. The next little bit, we're always below the red dot, so I go above the red dot. And then we get to this section over here where we're always above the red dot, so we're below the red dot. And the very last bit, I'm always below this horizontal asymptote but positive, so when I turn upside down I'll always be above and always positive. So I know it goes through all of those sections there. All right, is that enough to turn it into it? Oh no, one other thing. We haven't done calculus yet, and when we do I can prove this. But this is the reasoning why. The derivative of 1 over function x would end up being this thing, minus the derivative on the function squared. What it basically means, any stationary points, so those turning points, will still be stationary points or turning points. The y value might be different, but the x value will be the same. So on mine, well, I conveniently placed this one at -1, so it stayed there. But this one up here, it's above the horizontal asymptote, so I'm going to plot it about there. Again, I'm just estimating, I guess, where it is without an actual function. That's the best I can do. I think that's enough information. I've got to stay in those shaded areas. I've got to go through those dots. There's my red curve. So that's what well, it's a sketch, it's a rough sketch of what the reciprocal of that original graph would be. Let's get rid of the blue one so we can see it in a bit more detail. So there it is. The little strange thing there is that point discontinuity, but that would be our reciprocal graph. Alright, 5C. Gosh, there was a lot of theory for just a few questions, but there you go. We'll have a look at 5C.